Hello everyone and welcome back. So far in the last video, we built the foundation of our GPT model. We set up the dataset, trained the tokenizer, and even coded the self-attention layer. Today we're going even deeper. By building the transformer block, we will stack them into our full TinyGPT model, and we will set up the entire training loop. We will also include the optimizer that will help the model learn efficiently. By the end of this video, we will have a complete trainable GPT architecture. So if you're ready, let's begin. So let's start with the transformer block. A transformer block is like a Lego piece that we can stack together. Each block has two parts, a self-attention and a feed-forward neural network. The self-attention helps the token look around and see the other tokens, and the feed-forward network processes that information further. We can wrap both of them with layer normalization, which will stabilize their training and establish connections, which will help information flow throughout the network. By stacking multiple blocks together, the model becomes deeper and more powerful. So let's create a transformer block. We can go ahead and type out class transformer block. Give it the parameters of NN module. Define init self d model number of heads and we put here DFF and dropout. Then we can call the super init function to initialize. And basically, inside each block, we will normalize the input. We will now run the self-attention and add the connection. Then we'll do the same thing with a small neural network called the feed-forward layer. The residuals will help the model remember information instead of losing it. And now you will see that we'll add a layer norm function that keeps activation stable so the training doesn't blow up. Now let's code that. We can go ahead and type self.learn1 equals nn.layer norm d model self.ln2 equals nn.layer norm. First, actually, we should add the self.attention. The casual self-attention function we created last video. Add the parameters, the model, and heads and dropout. Now we can make the self.ln2 equals nn.layer norm the model. Then self.lp equals nn.sequential. Now for sequential, we can type. We will type the parameters inside this function, which will be nn.linear the model DFF GLU linear the model, and finally nn.dropout dropout. Now we'll have to define a forward function, which I will explain in a bit. Define forward self x x equals x plus self.attention self.ln1 x. Basically, we're adding the self-attention here. Now, let's add the feed-forward network. X plus self.mlp self.ln2. And finally, return x. So basically, every block takes what the previous one produced and mixes in the attention and nonlinears, and then pass it forward when it's done. When we stack multiple of these blocks, the model builds up a deep understanding of patterns in the data. Now it's time to move on to the TinyGPT model, which will use all the pieces we just made throughout the code. First, we will make the embeddings for the tokens and one of their positions. These embeddings will turn the token IDs into vectors, and then the positional embeddings tell the model where in the sequence each token is, because by default the transformers don't know the sequence. Then we add the token vector and the position vector together and send them through the stack of transformer blocks we just made. At the end, we apply a linear layer that projects the hidden state back into the size of the vocabulary. This will give us a score for every possible next token, and the most matching or most fitting token will be selected automatically by the model. We can also provide target tokens and calculate the cross entropy loss, which tells us how good these predictions or how efficient these predictions are. So let's first initialize the class and TinyGPT. Let's go. So we'll write class TinyGPT. The parameters will be NN module again. Define init self CFG and GPT config. Then we'll write self CFG equals CFG self dot token embedding, and then embedding we'll put CFG vocab, we'll put the CFG vocab size and the CFG model. CFG vocab size and CFG.d model. This is the token embedding that we are creating, as I mentioned earlier. And now we'll create the positional embedding, which will be self.positional embedding equals nn.embedding CFG block size CFG once again D model. Okay, this will be the positional embedding. Now we write self.drop nn.dropout CFG.dropout self.blocks equals nn module list. Let's put transformer block we'll put transformer block CFG model CFG dot number of heads CFG dot PFF and CFG dot dropout and close the parentheses. Then we will make a for loop for a dash in range cfg dot number of layers we should actually put this inside the parentheses. There we go. Now we'll make this self.ln f equals nn dot layer norm cfg.d model self.lm head equals nn.linear cfg d model cfg vocab size bias equals false, and self.lm head the weight, and self the token embedding weight. This will be the trying out the weight of the tokens. Now self.apply self.init initialize the weights. Now we'll define init weight. But before I define the init weights, I want just to give a quick overview. So basically, with the definition we just made, the token embeddings will turn the IDs into the vectors, basically like in numerical form. Then these positional embeddings will tell the model where each token appears in the sequence, because the transformers don't have any like built-in sense of order. We will also tie the weights of the input and output embeddings. That means the same vectors used to read the words are also used to write them. Fewer parameters, and basically means that we'll have better generalization. Now let's make the initialize the weights. Define init weights self m if is instance m and then dot linear and then dot embedding and then dot initialize normal m dot weight mean equals 0.0. Let's put std as 0.02. Now if is instance m and then dot linear and m dot bias is not none, m dot bias is not none, we should actually yep, there we go, is not none, nn dot initialize zeros under m dot bias. So now we should make a forward function where we combine the token and position embeddings. We will pass them through our blocks and finally predict the logic for the next token. If we can provide the targets, we'll also calculate the entropy loss. And this is basically how the model learns which token should come next. It will look for the best possible token to choose from. So now let's define forward. Self idx targets equal none. bt equals idx.size token self. But basically now we should make token the vectors. Now we should make the vectors self.token embedding idx. And now we should make the position vectors. Position equals self.position embedding torch.arrange t device equals idx.device. This will be the position vectors. And now we should add and drop out. So x equals self.drop token plus position. We just made these. Now we make a loop for blk in self.blocks x equals blk x, which is the transformer block. Then we'll make x equals self.ln fx. This will be the final norm. Self.ln fx. So now we should make the logic for the predicting the next token. So we'll put logits equals self.lm head x. We will set the loss to none. And we'll say if targets is not none, loss equals f.cross entropy logits.view from -1 to logits.size beginning from 1 -1. And then we'll also add the targets view. Okay. So now we will return, like if otherwise, return logits and loss. Now now that we have made the forward function, we should make the generate function. And this is basically where everything happens. We will give it a starting prompt. It will predict one token at a time. It will change it, append it, and keeps going until we hit our limit. Then we'll have the temperature control, and this will be how random the output is. If we have a higher temperature control, it means the model will be more creative. Lower, it means it will be more focused. And the top K we'll make, which will keep only the most likely words to avoid nonsense. So let's go ahead and make the generate function. First we'll add the torch, no grad. Now define generate self idx. We'll put max new tokens to 100 for now. We will set the temperature to 1 and the top K, which is optional. These can all be changed according to your individual settings. So we can go ahead and make optional. And we also have to add the integers equals to none here. Okay. So now we can go ahead and write self.eval or dash in range max new tokens. So here it will run it 100 times, the loop. idx conditional equals idx that minus self.cfg dot block size, add logits equals self idx conditional logits equals logits. We'll add -1 in this divided by max temperature between temperature and 1 to the power of -6. Now if top K is not none, V equals torch.topk log its minimum between top K and log its dot size from -1. Then we'll make the threshold equals to V to -1 dot on squeeze we'll put -1 again. Now logits will equal to torch dot where logits lower than thresh torch dot full like logits, and we'll put -f. We'll put infinite and logits. Now we can add the probs equals f dot softmax logits dimension equals to -1. Next ID equals torch dot multinomial probs number of samples equals to 1. And then we'll add the ID torch.cat, let's say idx next ID dimension equals to 1. And now we return the idx. Okay, so basically with the generate function we just did, we will take the starting prompt, we will run the models to predict the next token, add it to the sequence, and repeat until we reach the desired length that we specify here. We will use the, as I said earlier, the two main components, which are temperature and top K. Temperature makes outputs more random, or more focused depending on the value. So higher usually is more random, lower is usually more focused. And the top K sampling limits the model to the top K, the top most likely tokens at each step, which is usually very useful for reducing the unnecessary words. And earlier we also made the weight, the extra weight typing. Basically, we tie these weights between the input embeddings and the final output layer. This means that the same vectors that represent words are also used when predicting these same words as outputs. It also reduces the number of parameters and often makes the language models more efficient. Next, we'll be teaching our model using the training loop. We will load our process dataset and we'll create some data loaders, build the model and train step by step. First, let's make the pre-train function. So we'll say define pre-train mpz path string sp model string TinyGPT out str, and we'll say block size equals 256. We'll put batch size as 64. B model equals 256. Number of heads equals 4. Number of layers, let's say equals 4. DFF equals to 1024. And then we'll have dropout as 0.1, learning ratio 3 to the power of -4, max steps is 2000, warm up is 200, grad clips equals 1. Now we will get the device, which will be, let's say, device equals get device, token equals to, let's say, SP tokenizer, and we'll put the SP model. Now we'll put CFG equals to GPT config. Let's say vocabulary size equals token dot vocabulary size. Then we'll say D model equals D model, number of heads equals to number of heads, number of layers equals to number of layers, DFF equals to DFF, block size equals block size, let's say dropout equals dropout. And we basically just defined the values of all of this just earlier. So now we will put the model, let's say, and we should actually put this here as and so let's say model equals TinyGPT CFG dot to device. Train ds equals next token dataset MPC path train and block size. Now let's make the value distribution. Next token dataset MPZ path, put value and block size. Train DL equals data loader train ds batch size, and we'll put equals to batch size, and we'll put the after the batch size we'll put shuffle equals true, and we'll drop the last as well. So we'll write drop last equals true. Now that we have added that, we now need to put the value DL equals to data loader val ds batch size equals batch size, shuffle equals false, drop last equals true. Okay, and now we'll put the optional. We'll put torch dot optim Adam W. The Adam W is basically the most commonly used version. Model dot parameters equals LR, weight decay equals 0.1. So here we use the Adam W optimizer. This is the standard optimizer for transformers and the cosine learning rate schedule. We also use the mixed precision if a GPU is available to make the training faster. So basically, we will, as if we put it into steps, it will be forward the pass to get the loss, then backward pass to compute the gradients, then optimizer to update the weights, and then we will occasionally evaluate the validation data and save the best checkpoint. And this loop will show a live progress bar with loss values in the command prompt. When we do it later, we will be able to see this progress bar and we can watch the learning happening in real time. So let's make the learning schedule as well. So after we're done with this, we'll type define learning schedule, put step, then we'll write if step is less than warm-up, return learning rate multiplied by step plus 1, and then divide this by warm-up. And then progress will be equals to step minus warm-up, and we'll divide it by the maximum in the range of 1 and max steps minus warm-up. And we'll return learning rate multiplied by, we'll actually do 0.1 multiplied by learning rate, and we'll do, yes, the remaining 0.9 multiplied by learning rate multiplied by 0.5, which will be multiplied by 1 plus math.cosine math.pi multiplied by the minimum between progress and 1.0 . Okay, and now we will put the scalar equals to torch dot amp dot gradient scalar, and we will put it as sudo enabled equals torch dot sudo dot is available, and add the step equals to 0, best value equals float infinite, progress bar equals QQDM, total equals max steps, and description we'll put as training, or we'll put pre-train. This will all be shown in the command prompt later on when we are training the model. Then we will add a loop while step is less than max steps for xb yb in train DL model.train xb yb equals to xb.to device and yb2 device. Then we'll add for program in optimal.parameter groups, and we'll say program learning rate equals to learning schedule, and give it step. And then we can put the optimal of the zero gradient. Optimal zero gradient, and we can also set to none equals true. So it will automatically be set to true or set to none. Then we'll put the width torch.amp.ollocast sudo enabled torch.sudo dot is available. So once we're done with that, we'll add loss equals to model xb and yb. xb and yb. Then we'll add scalar. This should actually be here inside the width. And we'll add scalar dot scale. Yes, scalar dot scale loss dot backward. And we'll also add if grad clips is not none, so if it exists, we will add scalar dot unscale opt dot, and then we'll also add torch nn.utils clip grad norm model.parameters grad clip. Now we can add the, here we'll add scalar.step, optimal, and if grad clip is not none, scalar dot unscale opt torch dot, and then utils dot clip grad norm model dot parameters grad clip. And then once again we'll add scalar.step. We'll add the if opt scalar.update, and we'll add step plus and equal to 1. So every time the loop is ran, at the end of the loop we'll get the step added to 1. So at the end, like each time we run the loop, we'll have a track of steps, and when we're at the max steps, the program should stop, or at least the loop should stop running. So now we'll write the progress bar dot set postfix. It should show the loss. Let's see, f loss.item to the third decimal. Now progress bar dot update by 1. Now if the step, the remainder of the division of the step by 200, which is the ones we determined is 200, but it can be any number, determining how much you choose on the max steps, is equal to 0. We'll put the value loss equals evaluate model val.deal and device. Then we'll write progress bar dot write f value loss at step, and we'll put value loss, and this we can put it value loss at the next 3 decimals. This will all show in the progress bar in the command prompt as well. And now we can say the if value loss is less than best val, best val is equal to value loss. And we'll save the checkpoint. Save checkpoint, model, CFG, token, checkpoint output. Okay. And now we have to check again once more if we are at the end of the loop. So we'll say if step is greater than or equal to max steps, break. Basically we'll stop the loop here. Now we will close the progress bar, put progress bar close, save the checkpoint, checkpoint output, save the checkpoint, and we'll also now print it so we can keep track of when where the checkpoint is saved and when it's saved. So we'll put okay. Saved checkpoint 2 and to the checkpoint output. And yeah, basically, now that we have done this, we will be able to, here we have saved the final checkpoint. So if I will have to explain it again, we will say that we used our training and validation datasets. We built a data loader for batching, and we initialized the optimizer. Then we used Adam W optimizer earlier. This is the most standard optimizer for transformers. And for the learning schedule, for the learning rate schedule actually, we made it start small to warm up, then it slowly decreases to stabilize the training. And when there's a training step each time, it does a pass. It does a check to compute the predictions. It calculates the loss, and then it does a background check to update the weights. So we also added a feature where if the device is using a GPU, it will run faster. And for every couple hundred steps, we check the validation loss and save the model if it's the best one so far, as we checked here. And finally, we will add the final checkpoint and print it out so we can know when its checkpoint is saved. And we will also see like most of this reflected in the command prompt later when we are training and testing the GPT model. So that's it for part 3 of our tutorial. Now we have our GPT model fully assembled and ready to train. In the next part, we will finally train the GPT model on Shakespeare's text and even use it to generate its own lines. If you've made it this far, don't forget to like the video, subscribe, and hit the bell notifications. Thank you for watching, and I'll see you in the next one.